Greetings to you once more, ladies and gentlemen. We are now going to tackle the rectangular coordinate system, something that you probably simply refer to as a graph. As I mentioned that, one thing you're probably going to want to get is some graph paper. If you've ever tried to draw a homemade graph, you'll realize how very unsatisfying and inaccurate it can become. I simply typed in under Google Images template for graph paper, and this whole thing came up. I ran it off, put in my major axes, and have myself a piece of graph paper. You literally will not need more than 5 pages, but it's going to be nice to have some just to do your rectangular coordinate system problems. So get yourself some graph paper. I think you'll find out that it helps a lot. All right, well, let's start with this guy. This guy is called the rectangular coordinate system, sometimes referred to as the Cartesian coordinate system, named after René Descartes, famous for his philosophy of realism, not too convincing philosophy, but the philosophy in which he summed it up by saying, "I think, therefore I am." Probably heard of that little catchy phrase. That was René Descartes, French philosopher of some renown, French mathematician of enormous renown. So René Descartes came up with this rectangular coordinate system. He basically said this. He said, you give me any equation, you algebra folks, you give me any equation in x's and y's, I'll draw you a picture of the thing on my graph. Likewise, you geometricians, you give me a regular figure on this graph, like a circle or an ellipse or a parabola or a hyperbola, and I will give you the algebraic interpretation of that in x's and y's. So he literally blended two types of mathematics, the concrete math of geometry and the very abstract math of algebra into something called analytical geometry. So anytime you and I take an equation, which we're going to do shortly, and draw a picture of the thing on this graph, we are practicing René Descartes' analytical geometry. A little background. Well, you're familiar with this look, right? You have these two bold lines. The horizontal bold line is called the x-axis. The vertical bold line is therefore the y-axis. And they cross at a very strategic point known as the origin. Now, one thing you're probably familiar with about these axes is that these are actually number lines. This is a horizontal number line. And as such, 1, 2, 3, 4, 5, the numbers to the right of the origin are positive, and the numbers to the left of the origin are negative. Likewise, this is a number line, and we designate that the values above the origin are positive, those below are negative. That's going to be important because you and I are going to be finding particular points on this particular coordinate plane. For instance, let's pick out a point. Here's a point right there. Now, every point is spoken of in terms of the origin. Origin, if you think of it outside of the realm of mathematics, means the beginning, the starting point, the reference point. So every point on this grid we will speak of in reference to the origin. This is my place of beginning. So to get to this point, I could go up 7 and to the right 3, or I could go to the right 3 and up 7. Both of those would get me to this point. But one thing you should know about mathematics is it is consistent. When we speak of this point in Moscow, Russia, in Seoul, South Korea, in Sao Paulo, Brazil. When we speak of this particular point, we always speak of it in one way. The left to right movement first, the up or down movement second. So to the right 3, and the right is positive, so positive 3, up 7, and up is positive as well, so positive 3, positive 7 is the name of that particular point. We call that an ordered pair of numbers, or just an ordered pair. And that adjective is significant. It's an ordered pair. The order makes a difference. Here's a good true-false question. The point 37 is the same as the point 73. True or false? Of course, that's false, because to find the point 73, I would go left to right first. That's the right. 1, 2, 3, 4, 5, 6, 7. Up or down next. Positive 3 is up. There's the point 73. So obviously, order makes a difference. Hence, we call it an ordered pair of numbers. Now, these two values, they have names. The first, the movement along the x-axis, which was positive 3, we call the x-coordinate. And, of course, similarly, this value, which is the movement along the y-axis, up 7, we call the y-coordinate. They have official technical names, but we're going to simply refer to them as the x-coordinate and the y-coordinate. All right, so we know that to look at a point, I start at the origin and do my left or right movement first, my up or down movement second, to find the name of this particular ordered pair of numbers. Check this out. These two axes, notice that they divide the grid, the plane, into 4 parts. Whenever we divide an area into 4 equal parts, we call them quadrants. Quadrants like quarter, a fourth of something. And these quadrants are named. It's kind of arbitrary, so get this straight. This one is quadrant 1. Moving counterclockwise, quadrant 2, quadrant 3, and nobody knows why, but this last one is called quadrant 7. 1, 2, 3, and no, that's not really true. It's called quadrant 4. But wouldn't it be interesting if that was quadrant 7? Wouldn't there be an interesting story behind that? But it's kind of boring. It's quadrant 4. All right, here's what we're going to observe. We're going to observe that the points in these particular quadrants have a particular makeup. For instance, every point in quadrant 1, positive, positive. Every point in quadrant 2, negative, positive. Remember to do the left or right movement first. Negative, positive. Every point in quadrant 3, negative, negative. And every single point in quadrant 4, positive, negative. So if I gave you a particular point, let's say the point 6, negative 2, and asked what quadrant that is in, you would say, well, let's see, it's positive, negative, it's positive, it's in this quadrant right here. Or you can simply find 6, negative 2, it's in this quadrant. So this is the 4th quadrant. And that's one thing Hawks will do for you. It's going to give you some points and say, hey, what quadrant is this in? All right. I'm looking at this grid, and I am focusing on, mentally, an infinite number of points that are not in any quadrant. Can you think where those points might be? They're not in any quadrant, but they're on this grid. Some of you are probably thinking, oh, I bet you're talking about the points on the axes themselves. Yes, I am. There are an infinite number of points on the y-axis, an infinite number of points on the x-axis. And they're not in any quadrant. They're in between quadrants, you could say. Well, let's make an observation about all of my x-axis points. Let's look at some examples, like 1, 2, 3, 0. 8, 0. -2, 0. Can you make a general observation about every single point on the x-axis? -2, 0, 3, 0, 8, 0. You're probably going, yeah, I see. All x-axis points have a y coordinate of 0. So whenever you see a y coordinate that's 0, 0, 0, 0, it's going to be on the x-axis. Let's make a similar observation about y-axis points. Let me pick out some. So 0 left to right, 0, 1, 2, 3, 4, 5. Here's 0, 5. 0, 9. 0, -4. Can you make a similar observation about all y-axis points? Well, let's see. 0, -4, 0, 5, 0, 9. I see the pattern. The x-coordinate of each point on the y-axis is 0. All y-axis points have an x-coordinate of 0. So bottom line, if you see a 0 at any point in your x or y axis, x or y coordinates, if either one of these guys is a 0, it's on an axis somewhere. And so when you see Hawks asking you, where is this point located, and that particular point has a 0 somewhere in it, it's not in a quadrant, it's going to be on one of the axes. All right, what else can we observe about this guy? That's a lot of information on one little grid here. All right. Hey, before we go any further, let's talk about something. Let's talk about the distance between 2 points. Let's talk about the distance between 2 points, let's say on the y-axis. Can you find the distance from 0, 5 to 0, 9? You could do it in a couple of ways. You could subtract 9 minus 5 and say, hey, it's 4 units. Or you could simply count 1, 2, 3, 4. It's no problem at all to find the distance between 2 points on a vertical line. Likewise, a horizontal line. How far is it from the origin to the point 8, 0? It's 1, 2, 3, 4, 5, 6. It's 8 units. So it's no problem at all to find the distance between 2 points on a horizontal line. But here's the challenge that we're going to be presented with. How do you find the distance between 2 points on a slanted line in which there are no units to count? I'm going to have to come up with another strategy to find a distance between 2 points on a line segment that is what we could call slanted. It's neither vertical nor horizontal. All right. First little hint here. Can you see in your mind's eye, as I draw this line segment here, Can you see in your mind's eye that there is a right triangle defined by this particular line segment? Can you imagine the right triangle? Some of you are probably seeing this guy right here. Right? There's a right triangle right there. I know it's a right triangle because it's the intersection of a vertical and a horizontal line. Now, ladies and gentlemen, as soon as you encounter a right triangle, some particular theorem ought to come to your mind. Does it? Hopefully, the Pythagorean theorem comes to mind. I will bet you cannot find a single high school or college level math book that talks about right triangles that doesn't mention Pythagoras, or that talks about Pythagoras that doesn't have a right triangle as an illustration. That's what the Pythagorean theorem is about. It's about right triangles. Do you remember what the Pythagorean theorem says? It says side squared plus side squared equals longest side squared. Side squared plus side squared equals the longest side, or the hypotenuse, the side opposite the right angle, squared. So this has got to be C in my Pythagorean theorem. The longest side is opposite the right angle. And it doesn't matter which of these is A or which is B. Hey, check this out. A is a horizontal segment. B is a vertical segment. I can find the length of a horizontal segment and a vertical segment simply by counting units. Here we go. 1, 2, 3, 4, 5. A is equal to 6. Oh my goodness. That was easy. And I can find this vertical distance by simply counting units. 1, 2, 3, 4, 5, 6. It's 8. Now here's the genius of the Pythagorean theorem. It says you give me any right triangle. I don't care if it's as big as this one or as big as the universe. You give me any right triangle, side squared plus side squared equal longest side squared. So that if I have any two of these letters, any two of these distances, I can find the missing third. I got two of them. A is 6, so this is 6 squared. B is 8, so this is 8 squared, equals whatever C squared happens to be. And that's what we're looking for. We're looking for the distance, C, between these 2 points, 3, 5, and 9, 13. Well, I can square this guy and that guy. And I can add these two together. That's C squared, but I'm not looking for C squared. I'm looking for C. So I'm going to take this square root of both sides. And I get C is 10. Hey, I got it. So without counting units, I use the Pythagorean theorem to find the distance of this slanted line segment. So here's the observation I would make. If you're given 2 points, here's how you can find the distance between those 2 points. Number 1, plot your 2 points. Number 2, connect them with a line segment. Number 3, draw the imaginary right triangle. Number 4, count your horizontal units. Number 5, count your vertical units. Number 6, substitute those into the Pythagorean theorem. Number 7, square each term. Number 8, add the two together. Number 9, take the square root of both sides. And in 9 easy steps, ladies and gentlemen, we have the distance between those 2 points. 9 easy steps. To which some of you may be saying, isn't there an easier way besides going through 9 steps to get the simple distance between 2 points? Yes, you're very insightful. There is. So here's what I want to show you. I want to show you how we can derive something called the distance formula. Please notice I have 2 points here and a segment connecting them. And I would like to find this distance between the 2 points. You go, well, what are the coordinates of those points? It doesn't matter. That's why I left it off of a piece of graph paper, is because the coordinates don't matter. All I know is that this is a particular point. It's a general point, so I'm going to call it x1, y1. That just means the first xy. I don't know this guy either, so I'm going to call it x2, y2. Okay? Points that we don't know, that we want to speak of in general, we just call points xy. Well, I got 2 of them, so I have to distinguish between the 2, calling one of them x1, y1, one of them x2, y2. Hey, we're going to do the same thing we did earlier. We're going to imagine a right triangle in which I have a horizontal line segment and a vertical line segment. Now here's the thing I want you to notice, and this is profound about this horizontal segment and this vertical segment. Go back to your other graph. Watch this. We found this length to be 6 units. We counted 1, 2, 3, 4, 5, 6. But please notice this distance is also the difference between your 2 x values. 9 minus 3 is 6. So this x minus that x will give me that. So x2 minus x1, whoops, that's a squared, is this distance right here. Whatever the x minus whatever the x will give me this distance right here. Likewise, make this observation. We counted 8 units here, good for us, but we can also find that this distance is 8 by taking the difference between my 2 y values. y2 minus y1 gives me 13 minus 5 gives me 8 as well. So in general, y2 minus y1 is the distance of this particular segment. How cool is that? So this segment is the difference in my x's, x2 minus x1. This distance is the difference in my y's, y2 minus y1. Well, look what we got. We have lengths of the 3 sides of a right triangle. That means I can express this in terms of the Pythagorean theorem. A squared plus b squared equals c squared. A squared plus b squared equals c squared. And that, ladies and gentlemen, is what you would call the distance squared formula. Yeah, but I'm not looking for a distance squared formula. I'm looking for the distance formula. So to find the distance formula, d, I am simply going to take the square root of both sides. Square root of d squared and square root of all this mess. Square root of d squared is just d, and the square root of all this mess is the square root of all that mess. There, ladies and gentlemen, is your bona fide, good housekeeping seal of approval distance formula. Now, I want you to know notice a very important thing here. When I take this square root of this right here, I don't get the square root of this and the square root of that. It is the square root of the sum of these two things. So do not try to take the individual square roots of that and of that. It's not the same. I have to square them, add them together before I take the square root. All right, let's practice using the distance formula. And in fact, let's use exactly the same 2 points that we did earlier. 3, 5, 9, 13. I'd like to find the distance between these 2 points. Hey, don't I need a piece of graph paper? Don't I have to draw a triangle? I don't. Not with my new handy-dandy distance formula. So the distance formula says x2 minus x1. Which one is x2? First thing you need to do, label your points. Doesn't matter which one's x1, y1, which one's x2, y2, but you need to label your points. Otherwise, you're going to get something mixed up. Notice how convoluted this is. X's and y's all over the place. So I'm going to call this guy x1, y1. And I'm going to call this guy x2, y2. Once again, I could have done it the other way. Doesn't matter. I chose it this way. So here's my distance. The distance is found by x2 minus x1, let's see, that's 9 minus 3 squared plus y2 minus y1, that's 13 minus 5 squared. Let's see, that's 9 minus 3 is 6 squared. Plus 8 squared. Hey, this is starting to look familiar. That's the square root of 36 plus 64. Yeah, that's the square root of 100. That's 10. Look at that. Instead of doing all of this, drawing the triangle, counting the units, plugging into the Pythagorean theorem, etc., instead of doing all that without even a single piece of graph paper, I found the distance between these 2 points with the distance formula. Pretty powerful tool right here. Hey, some of you are asking, and I know it's a good question to ask, what would have happened if I had reversed these two? If I had made this x2, y2 and this x1, y1? Let's see. Well, let's see what happens. Square root of x2 minus x1, that's 3 minus 9 squared. y2 minus y1, that's 5 minus 13 squared. Uh-oh, looks like we're going to get some negative numbers here. That's the square root of negative 6 squared plus negative 8 squared. Are we going to get a different answer? Oh, no. Negative 6 squared is, oh, yeah, it's a positive 36. Negative 8 squared is a positive 64. Look at that. I'm getting the same result. Doesn't matter which one you call x1, y1, which one you call x2, y2. You're going to get the same result. Why? What makes the difference? The squaring. You square a positive number, you're going to get a positive number. You square a negative number, you're going to get the same positive number. So it does not matter, this should be reassuring, it doesn't matter which one you call x1, y1, which one you call x2, y2. That's the distance formula. Hey, that came out nice and even, didn't it? Let's try one that doesn't come out so nice and even. fact, let's do these two guys. Here's what Hawks is going to do for you. He's going to say, hey, here's 2 points, find the distance. Here's 2 points, find the distance. So you're going to use your distance formula. First thing you're going to do, label them. x1, y1, x2, y2. Tell you what, if you don't label them, you're going to get something mixed up, especially when you have the same value with this opposite. You're going to get something mixed up. So I got x2 minus x1, that's 7 minus 2, squared, don't forget to square it, plus y2 minus y1, that's 10. Now watch this, 10 minus a negative 2, squared. Most of you realize, let's see, 7 minus 2 is 5 squared. Most of you realize that minus a negative 2 is plus 2. That's 10 plus 2. That's 12 squared. So I get the square root of 25 plus 144. I get the square root of 169. Some of you know what that is, others of you don't. This is where you're going to need your handy-dandy scientific calculator. Square root. Let's see, 169, square root, 13. Find your square root function key. You're going to need that. It's going to come in handy. That's 13. It came out nice and even. The distance between these 2 points is 13. Let's try this one. Again, x1, y1, x2, y2. So x2 minus x1, 5 minus 2, squared. y2 minus y1, 10 minus 4, squared. I'm going to get 5 minus 2 is 3 squared. 10 minus 4 is 6 squared. I'm going to get 9 plus 36. I'm going to get the square root of 45. Now, ladies and gentlemen, there are 3 ways to write this particular square root. The first is what you could call the radical. And that is simply to write it as the square root of 45. The second way to write this is you could call the simplified radical. Now sometimes radicals don't simplify, so these would be the same. This guy, however, simplifies. Let me show you how to simplify a radical, a square root. Square root of 45. First thing I want to do is express 45 in its prime factorization. That means I want to list it as a number of prime numbers multiplied. Now the way you're going to do that is something very familiar. Oh yeah, the old factor tree. Remember this? Think of 2 numbers that multiply to get 45. Some of you are thinking 5 times 9. Others of you are thinking 3 times 15. Either one of those would work. So let's say 3 times 15. Now, as soon as you get to a prime number, stop. You might remember a prime number is a number that is divisible only by 1 and itself. The only things that will divide into 3 evenly, 1 and 3. It's prime. The other number is not prime. Other stuff will go into 15 besides 1 and 15, right? So we call this guy a composite number. This is a prime number. Hey, keep going until it's prime. So what will go into, how can I think of two numbers that multiply to get 15? Only one way, 3 and 5. Those are both prime, so I stop. So here's my prime factorization of 45. 3 times 3 times 5. Now when I'm simplifying a square root, do you know what this little index is right here, this little number that's not visible? There's an actual understood 2 right there. It's a square root. So I'm looking for a factor that shows up 2 times. I got one. It's 3. If something shows up twice, I bring it out of the radical once. So this simplifies to 1 3 on the outside. What's left on the inside? Just 5. So square root of 45 simplifies to the square root of 3 times 3 times 5. Hey, something shows up twice. Bring it out once. 3 square roots of 5 is the simplified radical. The simplified radical expression. On occasion in Hawks, you're going to have to simplify a radical into its simplified form. So 3 square roots of 5 is another way I can think of the square root of 45. The radical is square root of 45. The simplified radical, 3 square roots of 5. And then finally, thirdly, the decimal approximation. I'm going to have to use my calculator for that. So here's what I'm going to do. 45 square root. Let's see what I get. 6.7082039. It usually says to 2 decimal places. Let me go ahead and write out 3 decimal places. 6.708. Now, if I'm going to express this to 1 2 decimal places, I go to the 3rd decimal place to see if I round it up or not. This is 5 or greater, so this 0 rounds up to a 1. So this is approximately equal to, that's what that means, approximately equal to 6.71. So depending on what your Hawks asks you for, you are either going to express your answer to a distance formula, which by the way is always a square root, as either a whole number, congratulations, it came out a whole number, or if it doesn't come out a whole number, just the radical, the simplified radical, or the decimal approximation. It's going to be one of those, so get used to that. All right. Let's see what's next. All right, let's look at these same 2 points, 3, 5, and 9, 13. We know to find the distance formula, label them x1, y1, x2, y2, do square root of, and go through my distance formula. I know how to do that. I can use the same 2 points to find something called the midpoint. You can imagine in surveying or geography or in mapping or in architecture or in design, you're going to want to be able to find the middle of a particular line segment. It's going to be important. And I have what's called a midpoint formula. And it is so stinking easy. First thing you're going to want to do with these points is the same thing you did with the distance formula. Call one of them x1, y1, one of them x2, y2. Because the midpoint formula uses the same x1, y1, and x2, y2. Here's how to find the midpoint formula. Keep in mind that the midpoint is a point. That's why it's called the midpoint. So it has an x-coordinate and a y-coordinate. To find the x-coordinate, I simply average my x-coordinates. How do you average two things? You add them together and divide by 2. And my y-coordinate of my midpoint is simply the average of my two y values. So it's simply going to be y1 plus y2 over 2. There's my midpoint formula right there. Average your x's, average your y's, you got your midpoint. So let's do it. The midpoint is going to be x1 plus x2, 3 plus 9 over 2. The y-coordinate is going to be y1 plus y2, 5 plus 13 over 2. This is easy. 3 and 9 is 12 over 2 is 6. 5 and 13 is 18 over 2 is 9. The midpoint of this particular line segment should be the point 69. Hey, let's check it out. Let's find the point 69. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Yes! Not only is it on the line segment itself, it appears to be in the very middle of that line segment. So this 6,9 is my midpoint. Midpoint formula is something you're going to need, and Hawks will ask you to find the middle of a segment that joins two particular points. All right. Here's something else that Hawks is going to ask you to do. And you might be noticing I'm going through both notes and problems in this particular segment. So I will not do a problem video for this particular section. The problems are involved in the lecture notes themselves. Hawks is going to give you 3 points. This is where it's going to be very nice to have a piece of graph paper. You're going to plot your 3 points. You're going to connect them, and you're going to say, hey, it's a triangle. And then Hawks is going to ask you this. Find the perimeter, and you know what that means. That's the distance around find the perimeter of the triangle. Find the distance of the find the perimeter. How am I going to find the perimeter? Oh, I have a distance formula. That distance formula allows me to find the distance between any 2 points. So I can find, for instance, the distance between these 2 points. That would be what we might call distance 1. I could find the distance between these 2 points. That's what we could call distance 2. And I can find the distance between these 2 points. We could call that distance 3. So 3 applications of the distance formula, add them up, and I've got the perimeter. So here we go. Distance 1. Refer to your distance formula. It's between these 2 points. So it's going to be x minus x squared plus y minus y squared. Here we go. X minus x, that's 8 minus 1 squared plus y minus y, but check this out, 9 minus a negative 5 squared. That's going to give me 8 minus 1 is 7 squared. 9 minus a negative 5, that's 9 plus 5, that's 14 squared. That's 49. 14 squared is 196 plus 49 equals 245. Now, I'm wondering if this guy simplifies, because I don't think Hawks is going to allow us to put in a radical unless it is simplified. So let's see if 245 simplifies. Remember the idea here, the factor tree. One thing I know goes into 245 is 5. 245 divide 5 is, oh my goodness, 49. Prime, leave it alone. 49, 7 times 7, both prime. Looky there. I have something that shows up twice. Bring it out once. So this guy simplifies to 7 square roots of 5. So check to see if it will simplify, because I'm pretty sure Hawks will not take that. It will, if it's correct, it will give you a blue indication. Red means wrong, green means correct, blue means keep working. So you keep working until you get that. All right, let's do the other two distances. D2 is between this point and this point. So it's going to be x minus x, 8 minus 4 squared, y minus y squared. That's 4 squared plus 5 squared. That's 16 plus 25. That's 41. And you probably know that's prime. Nothing goes into 41 evenly. So square root of 41, we're finished. All right, I got one more distance. The distance between these 2 points, D3. Let's see. Let's do x minus x, 4 minus 1 squared, y minus y, 4 minus negative 5. I'm going to go ahead and put 4 plus 5 squared. 4 minus 1 is 3 squared. 4 minus negative 5 is 9 squared. 9 plus 81 is square root of 90. You think that simplifies? Let's find out. Obvious thing that goes into 90 is 9 and 10. Hey, neither one of those is prime. Let's keep going. 3, 3, 2, and 5. Those are all primes. And you typically write a prime factorization, smallest number all the way to largest. So it's 2 times 3 times 3 times 5. Hey, I got something that shows up twice. Yes, I do. Comes out once. 3 square roots of 2 times 5 is 10. My third distance. So as I find the perimeter, it is simply the sum of these 3 distances. So I would write for my final answer 7 square roots of 5 plus square root of 41 plus 3 square roots of 10. And Hawks better give me a smiley face on that one. That's how I find the perimeter of a triangle. Find the lengths of each of the sides with the distance formula, add them up. That's your perimeter. All right, one other thing Hawks is going to ask you is this. It's going to give you an equation in two variables. Notice this isn't just an x or just a y, it's got both. They give you an equation with two variables, and they say, find the missing coordinate for each of these ordered pairs. So these points are going to be on this particular line. And what that means is this particular x and y, whatever they happen to be, if I substitute in here, is going to give me a true statement. But notice in each of the points, something is missing. So here's what I'm going to do. I'm going to supply what I know and find what I don't know. Remember, this is the x, this is the y, this is the x, this is the y, right? So I know that y is 0. So in this equation right here, I'm going to rewrite it, except everywhere there's a y, I'm going to put a 0. Minus 6 times, not y, but what y is, 0, equals 12. Now 6 times 0 is just 0, so that's gone. So I get 9x equals 12. Divide both sides by 9. Divide each by 3, 4 thirds. So x is 4 thirds. What did I do? I supplied what I know in this equation and find what I don't know. I'm either going to fill in for the x or for the y and find the other one. Let's do the next one. In this next point, I know the x value. It's 0. So in this equation, everywhere I have an x, I'm going to put a 0 and find out what y is. 9 times 0 is just 0, so I get negative 6y equals 12. Obviously divide both sides by negative 6. 12, a positive divided by negative is negative, negative 2. So the y is negative 2. Next one, I know the x value again, it's 2. So everywhere there's an x, I'm going to put a 2. Fill in what I know and find out what I don't. I get 18 minus 6y equals 12. My y's are over here, so I'll get rid of the 18. I get negative 6y equals negative 6. Divided by negative 6, y is 1. In this one, I know my y, it's 5. So everywhere there's a y, I'm going to put a 5. Let's see, that's 9x minus 30 equals 12. Add 30. X equals 42. Divide both sides by 9. X is 42 ninths. Now it's going to say simplify these guys. So I wonder if something will go into both of these. Well, the only thing that will go into 9 is 3 and 9. 9 won't go into that, but I bet 3 will go into that. Turns out it does. It goes in there 14 times. So 42 over 9 simplifies to 14 thirds. All right. So Hawks will give you an equation with x's and y's, and it'll give you a point where one of the values, either x or y, is missing. Fill in what you know, find what you don't know. All right, that's 3.1, both notes and problems. Good luck.